First of all, I'm a teacher of high school. So most of your arguments for me are very far. But, and I have another difficulty, that is my English. So I apologize for it. I try to do better next time. But today I have some experience on teaching of distributive structures, so I want to communicate them to you. And I wrote something because I want to understand what I say. We often realized that an equation formulated for describing and predict the behavior of a specific physical system is used to describe a different one. As an example, today we have had many of this example. Langevin equation describes both the behavior of Brownian particle and the behavior of the rate of entropy reduction in a thermodynamical equilibrium. The symbol that represents the velocity in the case of Brownian particle represents the rate of production of entropy in thermodynamical equilibrium. This presence of analogies push us to find the classes of systems whose behavior can be described in a unified way, such this that is distributive structures. This is the definition of Prigogine, and as we know, these are chemical patterns, kind of the dissipative structure. What are the characteristics of dissipative structures? It is an open system. That means that exchange energy and matter with the surrounding space. It has, this is very important, a specific shape, like most of the things we know. It has an irreversible evolution, and it described and foreseen. It is described and foreseen by a mathematical model that we have seen today. First one, perhaps the first one, not so much, but the other was used very much today. And the other things you can read on it. So dissipative structure. The problem is how to teach it within the frame of constructivism. In the constructivism, the schemas are a unit of knowledge, each relating to one aspect of the world, including object, action, and abstract concept. So, the question is, if the student not possess the set, or if the knowledge of the student is not rich enough, and if the student has not schemas to assimilate the concept we transmit, what's happened? And is another problem the frontal class an efficient way to construct new schemas?
When you speak about student, here high school student.
Yes. So you understand that the prerequisites are very low, mathematical knowledge is low, so we have to adopt a special techniques, didactic techniques. So now I give you an example. There is a strong evidence that the best way to construct new schemas, new knowledge, is to direct or simulate the practical experiences. This is a proof that I propose you is the fact that the baby in preverbal age will learn the whole sensory motor knowledge of space and time before learning a language. So there are other ways to learn something. I propose you a typical experiment that can be made with the students for transferred the schemas that are right up. Equilibrium, irreversibility, macroscopic state, microscopic state, ergodici, probability and macroscopic and microscopic state, temperature, fluctuation, probability of macroscopic and microscopic state, obviously. This is a chessboard of obviously 64 pieces. Initially, we distribute the pieces on the chessboard, one for each square. Every square represents an atom, and every piece represents a quantum of energy. With a perfectly random extraction, but this is not true because we use computer or sometimes other instruments. With a perfect random extraction of two numbers, we locate an atom, and if the atom has a quantum, we put of energy, we put it on another atom, chosen with the same method. Chosen with the same method. Okay. We go on with this procedure for n steps, simulating the temporal evolution of real physics system. It's quite surprising to know, to discover that this system can reproduce all the classical thermodynamic, statistical thermodynamic of equilibrium statements. We have some data. This is the microscopic state, the initial microscopic state. There's after 20, I think, yes, 20 exchanges, and so on. We have here there are the numbers of exchange. Here there is the value of entropy, and here there is the number of microscopic states of the system. It's quite surprising to discover that the number is 10 to 34, 33, and there are only 64 square on the chessboard. This graph represents the entropy that the student can calculate with the spreadsheet, simple spreadsheet. This is like a Brownian motion. It means when the Brownian particle have a velocity, a big velocity, dissipate energy, then start the fluctuation, and this is perfectly the reproduction of this kind of system. The other one is how the student can establish a maximum of of entropy. I give to the student a special state, and the student change a quantum in every way it is possible. So we can see that this is a relative maximum, not absolute maximum. A relative maximum because we have made all this change, all the possible exchange. So the student can determine a state, a macroscopic state of maximum relative entropy. And on this state can fit the Boltzmann distribution. So now we can interpret this number as the temperature, not in this case because the energy is very low. There is only 64 quantum. But even in its state, the energy of an atom was 1. So this number is a fact of all the system. Even if in classical thermodynamics we consider the temperature only at equilibrium. Another simulation we made with the students is this one. We used in this case a map, because the differential equation is complex, but if we use a pendulum forcing adaptive, we can obtain the same results. And we can see a map as a one-caret section of a complex system of the differential equation. So the student can manipulate all this picture. Can calculate the value of the map. This is slightly modified value of each state, because you can calculate something that is like a Lyapunov exponent. If we this is a estimator, so we can choose the parameters like for having chaos. And as you see here, this is a pixie, this is a pixie. It says xi plus d, and this number is more or less the Lyapunov exponent of these two evolutions. You see, r square is always 0.2, but we use more or less the same method. And this is an example of time doubling for X. See, this is the initial state. Then there are two attractors, 1, 2, 3, 4, and the system jump from one to other in time, so students can understand how means attractor, how means doubling period, and so on. And this one is another experiment we made with the students. You will see we use only a spreadsheet, Excel in this case. This is a pendulum. And this is, the student choose the parameter of the force damper pendulum in such a way that we can show on the graph the sensitivity from the initial condition. And this is a phase space of two variables of the three that are necessary for the system. So the student can manipulate the space, the phase space, even if don't have no one asking to use it for something more. At the end, I have written here using statistical methods. What means for me using statistical methods? Don't mean what we know. Okay, use statistical methods in physics. I want this example can make you understand how I meant. Assuming that the outcome of measurement is located on a range, if the interval is subdivided in an interval, the entropy can be calculated like as the expression. But now P is the probability that the outcome of measurement fall into the I interval, but it is also a statistical index of the system, because it practically determinates. Okay, I have almost finished. Sorry again for my English.
Thank you.
How would I do that?
So you arrive to teach these topics to high school students?
Yes, for 3 years, for 35 years, still today.
At CISA we have had a neuroscientist, a very important one, Jacques there, who was the first, he was among the first to understand that probabilistic concepts are innate, sort of innate. So they are present in small kids of the age of 2 months, 3 months. And I was surprised, I met him before he retired. So, and I was surprised, I saw one of the experiments, I was really surprised. So they point the laser to the eye of the kid. So if you are a parent, you should not bring your kids to his lab. So, and they try to understand if he pays attention to something. So, and so by the size of the kid. And so they show the kid, sort of on the computer screen, a system of balls, bounces. And at some point, so for instance, at some point there are, I don't know, 5 balls, over 10 balls, 8 balls that are blue and 2 that is red. Okay. Then at some point the blue ball gets out of the box. Okay. And the kid's paying no attention. But if a red ball goes out of the box, so the kid pay attention. So it's sort of considered sort of strange or improbable that the red ball gets out of the box. So this was done several years ago. So this experiment dates back to maybe 30 years ago, the first one. He was the one who started this type of experiments. And of course they have been reproducing using several means. And from time to time you read news on everywhere about the discovery of new types of these. But together with probability, maybe other concepts are innate. But for us, maybe it's important to know that there is an important innate effect in our probabilistic view of why things happen or do not happen. It's interesting. I don't know. I wanted to report this because you mentioned at some point in one of your slides you had some mention of this.
About the newborn.
Huh?
No, sorry.
About babies.
I can add this. How to explain to the student what is the irreversibility. And when the students stay 2-3 hours exchanging pieces on the chessboard and mind what he are doing, I think he gained deep knowledge, knowledge of what is irreversibility, the impossibility of return to the initial state. And when the student watches the number of states, can say, okay, if I play Totocalcio, I know if I play Totocalcio, it is impossible that I do 13, and it is possible that I don't do, it is more possible that I don't do 13. So it is clear for the student at this moment.
Okay, so that's thank you again.